So far, we've developed examples that show how material and energy balances can be used to model some simple chemical or biological processes, such as a blending tank and this example of the heated tank that we looked at in the last video. These models were developed using what we call balance equations that account for the accumulation of some quantity of interest based on the rate at which it enters and leaves the vessel and the rate at which it's generated or consumed. For total mass, the rate of accumulation is the time derivative of the density multiplied by the volume, and the rate at which material enters and leaves is measured either by the sum of mass flow rates, and our textbook frequently uses the lowercase w to indicate a mass flow rate, or density times volume flow rate, and our textbook often uses Q to indicate volume flow rates. The balance equations for chemical species can be obtained by multiplying the masses by mass fractions for particular components. Our textbook will use X for mass fraction. We can also perform species balances on a mole basis using volume times molar concentration. Our textbook also sometimes uses Y for mass fractions if the phase of interest is a vapor or gas phase. In this class, when we discuss energy balances, we're primarily concerned with thermal energy balances or enthalpy balances. And so we'll use notation that we've already introduced in the previous lecture. H hat represents the enthalpy per mass, which can also be represented by a heat capacity multiplied by a temperature or temperature difference. When accounting for enthalpy entering or leaving, we may also need to account for heat transfer, which will be indicated by a capital Q, and fluid work, which will be indicated by a capital W. Since mass is not generated or consumed by chemical or biological processes, the generation and consumption of mass will always be zero. When writing balance equations for chemical species, whether they're written as mass or mole balances, we may need to account for generation and consumption terms. Little r will represent a volumetric rate of reaction. So that must be multiplied by the correct stoichiometric coefficient to determine the molar production rate of a particular species in a reaction. If there are multiple reactions, of course, the generation and consumption terms should be summed over all of the reaction rates. And as you know, the production rates of chemical species can be related by the ratios of their stoichiometric coefficients, so sometimes stoichiometric ratios might be used. Energy, of course, is also a conserved quantity. It is neither generated nor consumed by chemical and biological processes. When writing model equations for chemical and biological processes, we sometimes also have to invoke other relationships, such as constitutive equations. These can be used to parameterize balance equations. We might use reaction rate laws, equations of state, phase equilibria, or transport phenomena models like Fick's law. Let's develop a model for a process that involves a chemical reaction. Here we'll consider a first-order exothermic isomerization reaction that has Arrhenius-like dependence of the rate coefficient on temperature. It's a first-order reaction, meaning that the chemical reaction rate is directly proportional to the concentration of one of the reactants. We'll assume that this chemical reactor is perfectly mixed, has constant volume, notice that the effluent is an overflow line in the drawing, has constant density, and we'll assume that the cooling medium temperature is the same everywhere. The rate of heat transfer, capital Q, between the cooling coil and the reactor contents will be given by a heat transfer coefficient multiplied by an area, and the temperature of the cooling medium minus the temperature of the fluid in the reactor. We'll neglect any heat of mixing or shaft work. The component A balance says that the accumulation of component A should equal the difference between the rate at which A enters and leaves minus the rate at which A is consumed according to the reaction. Since the stoichiometric coefficient in this reaction is 1, there's an implied 1 in the consumption term. Since we need to know the temperature in order to calculate the reaction rate, temperature is also important, and we should write an energy balance. This energy balance has already been simplified. The accumulation of thermal energy is accounted for by considering the difference between what enters and what is already in the reactor, and the change in enthalpy of the material between when it enters and when it leaves, plus the rate at which thermal energy is removed by the cooling medium. Our model is now a set of two nonlinear ODEs. We'll probably solve it numerically using the ODE solvers in MATLAB. It would be good practice for you to do a degree of freedom analysis on this model. Next, let's look at a fed batch bioreactor. In this fed batch bioreactor, we'll consider this pseudochemical reaction whereby some limiting substrate is converted to cells and products by the action of living cells in the reactor. The growth of the microorganisms in the reactor is described by a non-elementary rate law. Here, X represents the mass concentration of cells, S represents the mass concentration of the limiting substrate, and P represents the mass concentration of the products. Mu is called the specific growth rate, and Ks is the mono constant. We'll write balance equations for the cells, products, and the substrate. The rate of accumulation of cells is given by their rate of generation, which is the cell growth rate R sub G. The product accumulation is also related to the cell growth rate by a ratio capital Y sub px, where Y sub px represents the mass of products produced for every mass of cells produced. Substrate is being fed to the reactor and is consumed when cells are produced and when product is produced. Finally, because this is a fed batch reactor, the total volume of material in the reactor is not constant, and we need a total mass balance that accounts for the rate at which material enters the reactor. Note that when chemical reactions involve multiple species, the species mole balances are related by reaction stoichiometry. In this case, we don't have molar stoichiometry, we just have pseudo-stoichiometric ratios that represent the ratios of the masses produced or consumed by the reaction. The total mass balance is not linearly independent from the sum of the individual species mole or mass balances. But in this case, we're only writing material balances for 3 of the many species that might be in this reactor. So we can include the total mass balance in addition to these 3 component balances. So far, all of the processes that we've looked at have been perfectly mixed. In the next example, we'll consider a staged process. This is a 3-stage absorber, which is not perfectly mixed. The compositions of the material on each of the 3 stages inside the absorber are different. Furthermore, on each stage there's both a liquid phase and a gas phase. The liquid flows down from the top of the column, and the gas, or the vapor phase, bubbles up from the bottom of the column. We'll assume constant liquid and gas stream flow rates, which are given by L and G, and constant liquid holdup on each stage. The composition of the solute of interest in the liquid phase is given by X, and the composition of the solute in the vapor phase is given by Y. The subscripts indicate each of the stages, with F for the feed of liquid or the feed of the gas. On each stage, we'll assume that an equilibrium is achieved and that the solute composition in the vapor phase can be approximated by a linear relationship with the solute composition in the corresponding liquid phase on the same stage. Now we can write a component balance for the solute on each stage. The left-hand side accounts for the accumulation of the solute in the liquid phase on the ith stage. The terms on the right-hand side are the rate at which the solute enters and leaves in the gas phase and the rate at which the solute enters and leaves in the liquid phase. We can use our vapor-liquid equilibrium assumption to eliminate the vapor phase mole fractions. Since there are 3 stages in this operation, this equation actually represents 3 different equations, one for stage 1, one for stage 2, and one for stage 3. So our model for the 3-stage absorber has 3 component balances, one for each stage. These equations, of course, are highly coupled, so it may not be easy to eliminate variables and write this as a single higher-order ODE. In the next video, we'll consider one last example of a process that is not perfectly mixed. And then we'll summarize what we've learned about process modeling using balance equations from chapters 1 and 2 of the Seaborg text.